Thanks for tuning into my talk. My name is Jake Seeley. I'm a postdoc at the Harvard Center for the Environment, and I did this work with Nader Jeevanji from GFDL. So the title of my talk is H2o windows and CO2 radiator fins, a clear sky explanation for the peak in ECS. This talk is about the state dependence of equilibrium climate sensitivity. And you might not be used to thinking about ECS as a state-dependent quantity, because when we talk about ECS, we're most often focused on the pre-industrial Earth. You take the pre-industrial Earth with a surface temperature of 288 Kelvin, double carbon dioxide, and the equilibrium warming you get is what we could call the pre-industrial ECS. And of course, that's the most immediately relevant quantity to humans living today. But if we take a broader view, we can easily define ECS for other base states. So there's actually some curve like this that relates the amount of CO2 in the atmosphere to the global mean surface temperature. And if we know this curve, then we can calculate the ECS for any base state by simply doubling the equilibrated CO2 concentration and then finding the corresponding warmer surface temperature. So we could do that for a cold base state with low CO2, or we could do it for a warmer base state with higher CO2. It's the same procedure. And a number of studies have systematically explored this state dependence of ECS, and they find something really interesting. This figure is from David Roms's paper from 2020, which looked at the ECS in a cloud resolving model. And along the x-axis in this figure is the surface temperature, and the y-axis is the ECS plotted at each surface temperature. And what you see is a peak in the ECS at a surface temperature of around 310 Kelvin. So that's quite hot. It's hotter than the tropics today, but it is potentially relevant to interpreting the paleoclimate record. And it's also related to the question of whether you can induce a runaway greenhouse by adding CO2 to the atmosphere. So the ECS peak has been seen in other types of models. It's been seen in global climate models and even in 1D radiative convective models. And since I know this talk is recorded and you can pause it, I've just put a few links in the upper right of this slide. The first link is to a recorded talk by David Romps about his 2020 study. And the other is a link to Nick Lutzko's blog post that provides a really nice summary of previous literature on this ECS peak. So that's just for your reference if you want to read more background. So we've seen that the ECS peak is observed in models across the hierarchy, and that suggests that there's a robust physical mechanism present in all of these models. So we set out looking for a clear sky explanation for this ECS peak. And to do that, we used really the simplest model in this hierarchy. And that's what this talk is about. So let me first give a quick overview of the model that we used. It's a one-dimensional model with an assumed thermal structure. We have a moist adiabatic troposphere capped by an isothermal stratosphere at a fixed temperature. And for radiation, we used a line-by-line code called the RFM, which was developed by Anu Dudia. And so we've got all the spectral information you could want about the long-wave fluxes in our model. And we study CO2-induced warming in this model simply by imposing TOA energy balance for varying concentrations of CO2. And we end up with this curve that relates the CO2 concentration to the surface temperature. And then, as I showed you before, it's straightforward to calculate the ECS for any base state along this curve. And this is what comes out. As a function of surface temperature, the ECS in our simple clear sky long wave only climate model increases from less than 2 Kelvin for cold base states to over 5 Kelvin at surface temperatures of around 310 Kelvin. But then the ECS declines at still higher surface temperatures. So this is great. We have a very simple climate model that reproduces this peak in the ECS. And that means we can dig in to understand why this peak exists. So a good starting point is the standard forcing feedback framework for ECS. It says that the ECS is given by the ratio of the radiative forcing from doubling CO2, which I'll denote by F2x, to the climate feedback parameter, lambda. And we can easily apply this framework to our model. Here's the ECS peak on the right. And on the left here is the CO2 forcing calculated at each point along this curve. And what you see is that F2x, the radiative forcing, increases monotonically as a function of increasing TS and CO2. So this forcing curve contributes to the initial increase in ECS, but it can't possibly explain the peak because it's monotonic. So that really leaves the feedback parameter, which does indeed have a minimum at around the same surface temperature as the ECS peak. So it's this minimum in the feedback parameter, which is where the model's radiative spring is the weakest, or where you get the least amount of additional OLR per degree of surface warming. That minimum is responsible for the peak in ECS. And so that's what I'll focus on for the rest of this talk. Now, to understand the minimum in the feedback parameter, we're going to look at feedbacks through a prism. In other words, we're going to use that spectral information that we get from using line-by-line radiation. So here's what we do. We take a base state and we calculate the spectral OLR. And then we add a moist adiabatic temperature perturbation, so 1 Kelvin of surface warming and the associated moist adiabatic tropospheric warming at fixed relative humidity. And then we recalculate the spectral OLR, and then we just take a difference between those two spectral curves. And that's the spectral feedback decomposition. It highlights the parts of the spectrum in which more radiation escapes to space when the system warms up. And of course, if you integrate this curve over wave number, you just get the total feedback parameter. So let's take a closer look at the spectral feedbacks for a base pre-industrial climate at 288 Kelvin. And for reference, I've added in the dashed line showing the surface Planck response. So this is the increase in spectral OLR that you would get through a transparent atmosphere. And the thick line is a smoothed version of the actual spectral feedback, which you can see falls short of that surface response due to the presence of greenhouse gases. And we can actually identify some key features here with the two most important greenhouse gases, water vapor and CO2. So first, I've added a gray line here showing the spectral feedback calculated with only H2O in the atmosphere, so without CO2. And I filled in with blue shading a portion of the spectrum where, at this surface temperature, H2O is optically thin. And this is often called the water vapor window. And you can see that this is actually the part of the spectrum where the feedback is the strongest. This is where the surface warming can be communicated out to space relatively unperturbed. But there's another really interesting feature here centered around the 15 micron band of CO2. There are these twin peaks in the spectral feedback where the feedback is enhanced by the presence of CO2. It's larger than it would be with only water vapor in the atmosphere. And to borrow a term from Ray Pierre-Humbert, I'm going to call these features CO2 radiator fins. Now, it's a little counterintuitive how adding an additional greenhouse gas could enhance the spectral feedback. So to understand that, we need to think about the differences between H2O and CO2 as greenhouse gases. Of course, H2O condenses in Earth's atmosphere, and so its concentration is strongly constrained as a function of temperature by Clausius-Clapeyron. And this has some really important consequences. In particular for us, it means that H2O optical depths are approximately invariant functions of temperature. And so that means that once a wave number is optically thick with H2O, its emission level, or the level where the optical depth is around 1, occurs at an approximately fixed temperature. So you warm the surface, but you still emit to space from the same temperature. Essentially, you've decoupled the OLR from the underlying surface temperature. And this was realized a long time ago in the 1920s by Simpson. But a very different story applies to CO2. CO2 is well mixed in the vertical, and that means that CO2 optical depths are approximately invariant functions of pressure rather than temperature. So when you warm the surface and the atmosphere, the temperature at a given pressure level increases. And that means that the CO2 emission levels also warm. So at wave numbers that are optically thick with CO2, when you warm the surface, the OLR can still increase. And that's how adding CO2 can enhance the spectral feedback. And since this talk is recorded and you can pause to linger, I've just put a quick summary of those arguments on this slide. I'm not going to read them now, but feel free to pause and absorb that material if you need to. So let's look at the evolution of the spectral feedback as surface temperature and CO2 increase. In each panel on the left here, I'm plotting the spectral feedback. And again, I'll shade the H2o window and CO2 radiator fins. And on the right is the spectrally integrated feedback, but decomposed into contributions from those two terms. So I'll play this animation a few times and pause to talk over it. So you can see that there's a transition happening in the character of this spectral feedback. At lower surface temperatures and lower CO2 concentrations, the feedback is dominated by the H2o window. And you can see that in the spectral integral, it's mainly blue. But at higher surface temperatures, water vapor has filled up in the atmosphere, and there really aren't very many portions of the spectrum where water vapor is optically thin anymore. And if it weren't for the presence of CO2, that means that the climate feedback parameter would be heading to zero. You would be approaching a runaway greenhouse regime where warming the surface doesn't increase your OLR. But because of the presence of CO2 and those radiator fins, you're actually still able to stabilize the climate. And you can see that those radiator fins are becoming stronger and stronger at higher and higher surface temperatures. And in fact, by the end of this parameter range, they really contribute almost all of the spectral feedback. So we see that the minimum in the feedback parameter, and therefore the peak in the ECS, it really occurs at a handoff point between two different ways of stabilizing the climate. At lower surface temperature, you have the H2o windows, which are closing as surface temperature warms and they're running out of steam. And then the CO2 radiator fins are ramping up to full strength. And it's the handoff point between these two processes that gives you the minimum in the feedback parameter. Now, there's one last part of the story which I haven't explained, and that is, why do these CO2 radiator fins become so strong, so important at high surface temperature and high CO2? And the first reason is just that when there's more CO2 in the atmosphere, secondary bands of CO2 besides the 15 micron band start to become activated. So you're just expanding the spectral intervals where this CO2 radiator fin physics is active. But you may have also noticed that each radiator fin also grows taller at higher surface temperature, and that's because the upper tropospheric warming on a moist adiabat is increasingly enhanced at high surface temperature. So whereas at cooler surface temperatures, say 288 Kelvin, the upper troposphere warms maybe twice as quickly as the surface. At much warmer surface temperatures, it warms more like 10 times as quickly as the surface. So if you are a CO2 emission level in the upper troposphere, when the surface warms by 1 degree, you might warm by significantly more than that, and that allows you to crank out a lot more infrared radiation to space. So let me just summarize what I've said here. The ECS peak is reproduced in a 1D clear sky, long wave only climate model. And we were able to show that this peak in our model results from a minimum in the climate feedback parameter. And with a spectral feedback decomposition, we showed that that minimum results from a competition between decreasing emission through H2o windows and increasing emission from CO2 radiator fins. And to close out, I just want to bring it back to the model hierarchy. What's attractive about the explanation for the ECS peak that I've just given is that the physics it relies on, which are the clear sky greenhouse effects of water vapor and CO2 and the moist adiabat, that physics is in all of the models from the simplest to the most complex. But that doesn't mean that our explanation is the end of the story. In more complex models, there are additional processes like shortwave feedbacks and cloud feedbacks that could be playing an important role in the ECS peak. So I hope that our paper isn't the last word on this. And speaking of our paper, please keep an eye out for it. It's in review at GRL. It has the same name as this talk. And I thank you for tuning in. Thanks to the organizers for the invitation to speak. And I look forward to the Q&A.